All right, I think that we can get started. So welcome everyone to the first installment of the UQ Philosophy Seminar for this year. And this year we're gonna have Alex Paseau from the University of Oxford, and he's gonna be giving a very interesting talk, in my opinion, about his new book with Oxford University Press, One True Logic. And this talk is on the second part of the book, and it's going to be a defense of infinitary logic, which I'm very much looking forward to hear. So please, Alex, take it away. Yeah.
Thank you very much for the introduction, Guillermo, and thank you also for the invitation to speak today. It's a pleasure to do so. So my talk is why infinitary logic is genuinely logical, this is the structure. I'll give you an overview. I'll discuss pure versus applied logic, finitary and infinitary logic, give you some references, and then turn to the arguments. And I'll come back to the structure as we go along. So here's the overview. I'll aim to do what it says on the tin, show that infinitary logic is really genuinely logical. Okay, so in order to do that, I need to start by explaining what I mean by genuinely logical. I also need to explain what I mean by infinitary logic. And then I'm going to present the arguments, such as they are, for the genuine logicality of infinitary logic. And as you mentioned, the discussion will be based in large part on part 2 of the recent book that came out, that I wrote with Owen Griffiths, came out last year with Oxford. Okay, so to explain what genuine logicality is, let's think about the distinction between pure and applied logic. So logicians study a bewildering array of logics, a great many logics. Philosophers are more familiar with some than with others. They are brought up on propositional logic and first-order logic. They might then go on to study second-order logic, intuitionistic logic, relevance or relevant logic, various modal logics, and so on. But of course, you can study any logic that you like as a kind of mathematical system and derive some mathematical theorems about it. And logicians often, logicians do. But their meta theory, the theory that they use to study these systems, is usually much more narrowly circumscribed. It's usually something fairly orthodox, which is something like first-order Zermelo-Fraenkel choice set theory. It's not always exactly the first-order Zermelo-Fraenkel choice. It could be that minus choice, or minus some other principles, or with some more likely with some large cardinal principles. But it's more or less along those lines. Or sometimes it's a closely related system, maybe a class system, or a system that's in some sense equivalent to the system. So logicians are really quite are very open-minded when it comes to the logics that they study, but the logic that they use, or the logical system that they use to study the first-order systems, is usually one of a very small, closely equivalent set of systems. So, for example, suppose that you wanted to prove that some system X is consistent. That proof would only be acceptable if it was proved in a standard meta theory. An example here is Quine's NF. People are looking for a proof of that, and there's some claim that there is one, that system is consistent within a sort of standard meta theory. So what does it suggest? As it suggests that we should distinguish applied and pure logic. And this distinction is familiar from mathematics, from the sort of development of mathematics in the late 19th century, which ended up distinguishing between pure and applied geometry. So roughly speaking, pure logic is the study of logics from a mathematical point of view, and pure logicians can be interested in any logic whatsoever. Just as in pure geometry, you might study what follows from some geometric axioms. There can be any axioms whatsoever. It could be spherical, hyperbolic, Euclidean geometry, or whatnot. Applied logic, however, is the study of what really follows from what. And so applied logicians are interested in logical consequence among statements. So this is a bit like applied geometry, and the study of the geometry of our world, or worlds perhaps like ours that share its laws, right? So that would typically be interest mathematical physicists as opposed to pure mathematicians. Priest calls applied logic the canonical, Graham Priest calls this the canonical application of logic to logical consequence. And so today is going to be an exercise in applied logic. Okay, we're interested in what really follows from what. Some people call this foundational logic, or studying the correct logic, what the correct logic is, or logic that is genuinely logical. I've used that in my title, or simply just logic. For example, think of the question, is second order logic really logic? The second occurrence of logic there is genuinely logical, right? The question is it really genuinely logical? Does it really capture what follows from what? Okay, so there's this pure applied sort of distinction in logic, which I, as I've explained, I think is close to universal in logical practice, and I think in kind of everyday thinking. And we're going to be interested in applied logic. The applied logician starting point is meaningful discourse. This is typically couched in natural language. So just to have some sort of homely examples, some natural language arguments are logically valid, others are not. So Fido's a dog, therefore there's a dog, strikes most people as logical. The conclusion follows from the premise logically, whereas the argument Fido is a dog, therefore there's a cat, is logically invalid. The conclusion does not follow logically from the premise, even though the conclusion is true, of course. So, of course, these examples are very homely, but we can include in natural language. I don't just mean sort of everyday language, and we can include arguments in mathematics, science, law, and so on under this heading. So what is the correct applied logic? Well, different logicians have gone different ways. Frege, for example, used second-order logic. And then over the course of the 20th century, first-order logic emerged as a kind of benchmark logic with some philosophical support, for example, and well, most famously from Quine, who claimed that first-order logic is the correct logic. And there's some sense in which first-order logic still rules, despite the fact that there's been a huge amount of interest in other logics, in that standard sort of meta systems, meta theories, logicians' meta theories are usually cast in first-order logic. And there is a trend in 21st century philosophy of logic for pluralism that actually is there's not just one correct applied logic, but there's many. And that's the debate between logical pluralists and logical monists. I won't really talk about that today, only very incidentally, because I think most of what I say will be independent of that. So a contemporary tenet of in the philosophy of logic, or thinking about logic, is that logic is finitary, and I mean applied logic, right? So any logically valid argument must be capturable in a finitary logic. And this is what I'm going to challenge. Okay, so I've explained what I understand my pure versus applied logic. Now I need to explain what a finitary logic is in order to answer the question I set myself about whether infinitary logic is genuinely logical, indeed showing that it is. So, before that, let me say a little bit more about the language that applied logicians should be interested in. So I said it's meaningful discourse, and that's typically cast in natural language. Is it really natural language? Well, it might be sort of a cleaned up version of natural language. At a very minimum, this means that it's shorn of ambiguity. You set aside ambiguity, or you disambiguate before you formalize and think about logical consequence, because sentences of natural language can be ambiguous. But there are other aspects of natural language sentences, for example, vagueness, that some people think should be cleaned up before we start thinking about what the correct theory of logical consequence is. Now that might be a step too far, because there are certainly people who think that vagueness requires its own logic. So the logic of natural language should be a sort of a logic that accounts for vague language. I'm actually not going to talk very much about that. I'm going to assume we've got some cleaned up version of natural language, and then take it from there. Most of my points will not be affected by that. The more important point for my purposes is that the choice of any natural language, even a natural language that encompasses all technical vocabulary, would be parochial. So natural languages such as English, for example, accrue words by the day, right? So let's think about, so it's thinking about English, a sentence like, I can't play my DVD on my laptop. That would have been incomprehensible to Victorians, to anyone living in the 19th century. So languages grow, and we can imagine future languages. We could imagine, for example, landing on a planet, outside our solar system or outside our galaxy, even at some point in the very distant future. Let's call it Adurfia. When we're there, we meet a new being, we christen it Adurf, and we meet a new species, which we call Zuvarks, I'll pronounce it, Zuvarks. And then, we extend our language, and the following is a valid argument in the extended language. Adurf is a Zuvark, all Zuvarks are friendly, therefore Adurf is friendly. So, obviously our language is kind of a result of a contingent linguistic inheritance, and it will be extended in the future, and even if it isn't, it could have been extended. And there's no reason to prefer English to some extension of it. So it seems like the applied logician should be interested not in any particular natural language, including technical parts, but in its extensions. Sure, I mean, they can give an account of logical consequence in English, and I mean, including technical parts, but that would be that would be somehow an incomplete account, because you need to think about extensions as well. There's something contingent about English. So we can distinguish a parochial project, what I call a parochial project, accounting for logical consequence among actual sentences of cleaned up English, or a more ambitious project, accounting for logical consequence among sentences of extensions of it cleaned up English, right? And as, of course, it's a pejorative label, but as I've explained, the parochial project really is parochial, right? Because there's nothing sort of unique or special about current English as it's spoken today, the dialect that we are speaking today on the 3rd of March, 2023. Now, of course, what does a possible extension of English mean? Well, some of them we can have a clearer grip on. For example, the Adurf examples the Adurf example that I gave. You extend it with a few words, Zovark, Adurf, and so on. But what would it mean to think about all the possible extensions of English? Well, maybe that's a kind of a staggering idea, an idea that it's very hard to get your head around. So perhaps a methodologically sounder approach that that will allow for reasoned debate is to stick to extensions of English that we have some grip on. Okay. Now, these can actually take us quite far. I mean, for example, you might think of, you might say, well, look, English has only has a countable infinity of sentences, and that's going to be right because it's got a finite lexicon, and its sentences are of finite length. So they can only name a countable infinity of cardinals. But there's no reason to limit our account of logical consequence to English as it is today. We can imagine an extension of English that's augmented with a name for any cardinal up to some infinite kappa, right? Maybe up to aleph to the aleph omega or something like that. And we can get a good grip on that language. It's not a language we could learn. It's not a recursively specifiable language, but it's a language we can nevertheless theorize about. For example, logicians do this all the time when they think about languages with large numbers of terms. For example, they think about first-order languages with a name for every real number. And although it's not a number that it's not a language that one can some direct sense speak, we can theorize about it. Okay, all right. So that was all pure versus applied logic. Now I need to tell you a bit more about finitary versus infinitary logic before moving to the arguments. Okay, so as I said, natural languages are almost universally regarded, and I include myself, as finitary. Okay, I said English has a finite lexicon and its sentences are of finite length. So a simple example of a grammatical rule of English would be, simplifying perhaps a little bit because there might be some complications, but roughly something like, if A and B are declarative sentences, then the conjunction A and B is also a sentence. But the infinitary version of this rule is not a grammatical rule of English. What would be the infinitary version? Just for countable infinity, if A1, A2, AN, and so on, countable infinity of sentences are declarative sentences, then that conjunction A1, NA2, and ... AN, and ... is a sentence. Now that I take it is not a grammatical rule of English, because English does not have infinitely long sentences. In contrast, an infinitary logic allows us to conjoin or disjoin infinitely many sentences and or quantify over infinitely many variables. So what are examples of finitary logics? Well, pretty much any logic philosophers are seriously interested in, pretty much any logic that you will have encountered: first order logic, second order logic, the usual modal logics, usual non-classical logics, and so on. Their sentences are all of finite length. What about infinitary logic? Well, the book that this talk is based on does things in terms of the logic FTT, infinity, finite theory of types, infinity. And I'll come back to that and say something about that briefly. But I'm going to, for today's purposes, I think it's simpler to present L infinity and modify the discussion accordingly. So the basic idea is that L infinity is first order logic, but generalized so as to allow the conjunction and disjunction of kappa formulas for any cardinal kappa, and quantification over kappa variables for any cardinal kappa. And when I say any cardinal, I mean finite or infinite. Okay, I'll specify the language a bit more carefully in a second. I won't do that for the semantics, because it's just a straightforward extension of the first order logic semantics, which I'll assume familiarity with. So for example, an infinitary conjunction is true in a model under an assignment if and only if each of the conjuncts is, right? So it's the obvious clause for conjunction there. And what about quantification? Well, the formula phi with the leading existential quantifier over some collection of variables. Notice it does not have to be a finite collection of variables, any collection of variables whatsoever, v1 up to vn and so on. Well, that's true in a model under an assignment if and only if there are elements of the domain a1, an, and so on, corresponding to the variables such that phi of a1 up to an and so on is true in the model under the modified assignment. So there's nothing sort of very funny going on there. It's just a kind of a generalization to a larger cardinality, both for conjunction and quantification. So in a bit more detail, let's think about FOL star, call that a first order logic with kappa many variables and kappa many relation function and constant symbols for every cardinal kappa. That's a very large language, class size language. It's also got parentheses and the usual logical vocabulary. We don't have to be too fussy about what that is, but we can say it includes the negation symbol, the conjunction symbol, and the disjunction symbol. In the infinitary context, you usually write conjunction disjunction as big wedge and big V when they conjoin or disjoin statements in a set. So the atomic formulas of FL star are defined in the obvious way, in terms of predicates and constants and variables. And then the grammar of L infinity is then given by specifying its class of well-formed formulas. This class C is the least such that, well, it has all the atomic FOL star formulas. It's closed under negation, so phi is in C, then not phi is in C. And then for any cardinal kappa, it's closed under kappa many, conjunction of kappa many formulas. Wedge phi is also a formula if phi is a non-empty subset of size kappa, and likewise for disjunction. And for any cardinal kappa, if phi is in C and V is a non-empty set of variables of size kappa, then for all V phi is in C and there exists V phi is in C, I've put the existential and the universal version there. Although I'd only mentioned the existential quantifier before. Obviously, it doesn't matter if we've got one, we've got the, we can define the other. Okay, so this is what the sentences of such a logic look like, and I've given you the semantics. So that's the kind of distinction between finitary and infinite that I'm interested in here. I'm not claiming that's the only sense of infinitary, but that's the dimension I'm going to focus on. And a very potted history of infinitary logic would notice that some of the early 20th century pioneers in logic used infinitary formulas. From about the sort of 1930s onwards, or late 1920s, logic became finitary, to put it in sort of broad terms. But before that, some of those pioneers like Hilbert, Levenheim, Skolem, Zermelo, and others used infinitary formulas, thought there was nothing wrong with using them. And then gradually, as I said, in the second quarter of the 20th century, first order logic emerged as a canonical logic, and that coincided with the falling away, the submergence of infinitary logic. Now, in the second half of the 20th century and into the 21st, there's been an explosion of philosophical interest in logics other than first-order logic, but they've almost all been finitary. They've all had sentences of finite length. Now, the way I've presented infinitary logic is its sentences are of finite length because the conjunctions or disjunctions or the quantifications are over respectively sets of formulas or sets of variables, but the effect is to quantify or conjoin over infinitary sets. That's permissible anyway. Now, infinitary logics have been a minor area of mathematical study since the 1950s. Maybe minor is a little pejorative. I mean, it's not a huge field, but they're not generally regarded as correct or genuinely logical. And the usual line, if they're thought about at all, is that they're purely mathematical interests. They belong to the realm of pure logic, not applied logic. Okay, so I disagree. I think infinitary logic is genuinely logical. Okay, so that was the setup. That's the first third of the talk, and the last 2/3 are going to be the arguments for the genuine logicality of infinitary logic. So I've explained what the title means, what the question is. Just to give you a couple of references, two pioneers here are Alfred Tarski and his posthumous "What Are Logical Notions?" A talk he gave in London in 1966, but published posthumously in 86. Guy Lasher, who's very much with us, has written about this, some very important work from The Bounds of Logic back in 91 to her most recent book, Logical Consequence. And the thing that the book that I'm basing my talk on mainly is part 2 of my book with Owen. The question we now turn to is why logic is infinitary, or the correct logic, or the foundational logic is infinitary. Let's think about the shape of the case. The shape of the case is made up of 2 sorts of considerations. There are bottom-up arguments, and there are top-down arguments. Okay, so what's the difference? Well, a bottom-up argument is a sort of relatively light theoretical principle. It's not some heavyweight sort of philosophical theory of what logic is or what the logical constants are, but sort of using principles that not entirely uncontroversial, but that many logicians would accept, or not using heavy mathematical, logical, or philosophical machinery, something along those lines. And that's roughly corresponds to chapter 5 of the book. And top-down arguments are more theoretical. They're based on the nature of logic and or the nature of the logical constants. And that's chapter 6 of true logic. And as I said earlier, the case that logic is infinitary is largely independent of the monism versus pluralism debate. In other words, it should be acceptable to most pluralists, I mean, not every pluralist, but who could read its conclusion as the true logics are infinitary, right? Or the true classical logic is infinitary. Maybe you're a pluralist and you think classical logic is one among the many acceptable logics. If you're convinced by these arguments that I'm about to give, you might conclude that the true classical logic is infinitary, or there might be other logics too, as you see it. In this book, we call this the Logos hypothesis for various reasons. I won't use that terminology here. Okay, so let's look at bottom-up arguments for the infinity of the infinitariness of logic, genuine logic. Here's an example of an argument that has been thought about in the literature that I think establishes the point. Let's think of it's an argument with infinitely many premises. The first premise is there's at least 1 planet. Second, there's at least 2 planets, and so on. There's at least n planets for every finite n. Okay, so it's got a countable infinity of premises, 1 for each natural number. And the conclusion is there are infinitely many planets. Okay, now it's clearly valid in some sense. Okay, if there's at least 1 planet, at least 2, at least 3, and so on, then they're going to be infinitely many. Okay, so that the conclusion will follow in some sense. The question is that a logical sense? Is it logically valid, or is it merely valid in some other way? So the argument for the genuine logicality, or genuinely logical validity of this argument's validity of this argument is fourfold. And I won't have time to go into the full claims. I'm just giving you the kind of sketch of the argument. The first claim is that the argument really is logically valid. Okay. So that requires some argumentation, as I said. The second claim is that first order logic cannot capture this argument. So this is an argument really to go on beyond finite tree logics, but just claim 2 does it in 2 steps. Claims 2 and 3 together do it in 2 steps. First order logic cannot capture it. Well, this is obvious because first order logic is compact. So a finite conclusion, a finite subset of the premises would entail the conclusion, but clearly it does not in this particular argument. The third claim is that other finite tree logics than first order logic cannot capture this argument or its generalizations. And again, that takes some work to show that. And the fourth claim is that an infinitary logic can. Okay, and that is obvious because the conclusion is just the conjunction of the premises. So if you allow countably infinite conjunction, then you can just conjoin all the premises and you get the conclusion. So a logic that allows infinitary conjunction or countably infinite conjunction at least will vindicate this argument as logical. So to give you an example of a non-formally valid argument for which you require infinitary resources, an argument such as this: Bob is not my parent, Bob is not my grandparent, Bob is not my great-grandparent, and so on. Then Bob is not my ancestor is the conclusion. So now this is not a formally valid argument. There's a missing meaning premise here that does make it formally valid, which is that you're my ancestor if and only if you're my parent, or you're my grandparent, or you're my great-grandparent, or so on, where this list continues ad infinitum. So the way that you would formalize the Bob argument plus the meaning premise in an infinitary logic is you'd say not P1b, standing for Bob's not my parent, not my parent, not P2b, Bob is not my grandparent, not P3b, and so on. And then the meaning premise would be you get to be my ancestor if and only if you're either my parent or my grandparent or my great-grandparent, and so on. So you've got an infinite disjunction there. And then the conclusion is that Bob is not my ancestor. So that's what the formalization of the Bob argument would look like. And the infinitary logician thinks that you can explain quite easily how this argument gets to be valid in terms of the meaning premise and the resources of infinitary logic. Now, continuing with bottom-up arguments, let's think about superhumans who can accomplish super tasks. These are infinite tasks that are performed in a finite amount of time. So by speed up, they're capable of uttering, these superhumans are capable of uttering infinitely long sentences, such as 0 is even, and 2 is even, and 4 is even, and ... 2n is even, and ... Now, that's an infinitely long sentence that human beings cannot utter. We can describe it, but we cannot utter it ourselves. The way superhumans do it is, they take half a second to utter 0 is even, and then a quarter of a second to utter and 2 is even, and then an eighth to utter and 4 is even, and so on. So after 1 second, they've said the whole sentence. So given this capacity of theirs, and there's no reason to think that superhumans are impossible, we can perfectly well imagine them. It may be that there's physically possible. That will depend on some issues on the interpretation of physics, but whether they're physically possible or not, they're clearly, fairly clearly metaphysically possible. Let's imagine them performing the following inference. So they utter the sentence that I just mentioned earlier, running through all the even numbers, saying that each of them individually is even. So this countably infinite conjunction, 0 is even, and 2 is even, and 4 is even, and so on. So they take a second to say that, then they pause maybe for another second, and then they utter a conclusion, and they take a second to say that, and the conclusion is 0 is even, and 4 is even, and 8 is even, and ... running through all the multiples of 4 this time, not the multiples of 2. Now, okay, so they perform this argument, they take 3 seconds to perform it, and it's an inference that drops the premises every other conjunct, starting with the second, right? What is it? Well, it's an infinite form of conjunction elimination. And the thought is that this inference is just as logical as finite tree form of conjunction elimination. So superhumans, for example, could explain to us what they've done, and they could they could say, it's quite similar to a kind of inference that we could perform, but that's truncated. Maybe we could truncate if you truncate the inference at 1,000,000, it would take us a very long time as humans to say the sentence, the premise, and to say the conclusion. But we could, if it's up to 1,000,000, we could do that. We could do it. It's a practical possibility for us to do it. Well, for superhumans, the infinitary version is a practical possibility. And we have to distinguish describing an inference from performing it, right? You might say, well, this isn't really an infinitary inference because look, we humans can describe this inference in finitary terms, and we can just explain that the conclusion follows from the premise in finitary terms. But that's not actually performing the inference, that's describing the inference. So what the thought experiment is to imagine the superhumans actually performing the inference in the way that you could just imagine us humans performing the truncated version of the inference, which goes up to 1,000,000. Okay, so the thought is that the superhuman inference is an infinite form of conjunction elimination, and it looks perfectly logical. There doesn't seem to be anything non-logical about it. It's just they're able to say an infinitely long sentence, whereas we humans are not. Now, there are more bottom-up arguments than the above, and I will give one more to come. But one thing to be clear about is that we're talking about implication rather than an inference, strictly speaking. In the case of superhumans, I talked about inference, but really this is a kind of a device, a sort of pedagogical device to get you to think about implication. So I want to distinguish between implication and inference. Implication is the relation that holds between statements. Okay, it is the logical consequence relation. Whether or not human beings appreciate it, whether or not superhumans appreciate it, and it's something. It's not an anthropocentric fact. It's just a relation between some sentences and another. Inference, however, is something that an agent performs. That is anthropocentric, even if we consider idealized agents. So superhumans are performing an inference, but if the inference that I described is one that respects logical implication, because if the infinitary logician is correct, if the thesis that infinitary logic is generally logical is right, then it is a valid implication. Now, I take applied logic's main role to capture implication. That's the business of applied logic. Or its main business. The study of inference, on the other hand, is something quite different. The study of inference and rationality is informed by logic. I mean, it's not entirely separate from logic, but it's not determined by it, right? So, for example, just to take a toy example, suppose that A implies B, and I believe A, and I come to realize that A implies B. Must I therefore believe B? Well, maybe not. It might be that B is so implausible that I come back to A and think, well, maybe I should revise my belief in A. Maybe it's not as credible as I thought, or maybe I should go back to the implication. Does A really entail B? I might wonder. So logic leaves all those questions open, right? Because those questions are about what rational belief, inference, and rationality. But logic itself just tells you that A implies B. Okay, so to come to another bottom-up argument, let's think about cardinality quantifiers. So quantifiers of the form, there are at least x many, where x is a cardinal. Or there are at least n many in the finite case, or at least aleph alpha in the infinite case. So let's think about second order logic, because the planets argument, some of you might have realized the planets argument is actually capturable in second order logic, because in second order logic you can say that there are infinitely many things, infinitely many planets, for example. So you might think that you don't need the power of an infinitary logic. You could do things in second order logic. So this is a sort of an argument from the perspective of the infinitarist perspective against second order logic being a correct foundational logic. And the argument goes like this. So think about statements like, if there's at least two things, then there's at least one thing. That's at the top of your table there. Is that a logical truth? Well, as long as you've got first order logic, you can formalize that, and then it turns into a validity. So yes, it's a logical truth, would be the usual way of thinking of it. If there's at least three things, then there's at least two things. Similarly, If there's at least n plus 1 things, then there's at least n things. Again, first order formalizable for any given n, finite n. Yeah, clearly a logical truth. What about if there are at least aleph 1 things, then there are at least aleph 0 things. Now, that can't be first order formalized, but it can be formalized in second order logic. So the second orderist who thinks second order logic is the correct logic, will be able to formalize that and vindicate it as a validity. So they'll think that that's a logical truth. Similarly, if there's at least aleph 2 things, then there's at least aleph 1 things. Similarly, for if there's at least aleph omega plus 1 things, then there's at least aleph omega things, because aleph omega is second order formalizable. But then at some point, they're going to run out. At some point, they're going to hit an ordinal alpha, such that aleph alpha, or there at least aleph alpha, is not definable in second order logic. Because second order logic, it's not hard to prove, will only define a countable infinity of these cardinality quantifiers. So let aleph alpha be the very first one that it cannot define. So when you get to, if there are at least aleph alpha plus 1 things, then there's at least aleph alpha things, the second orderist does not see that as a logical truth. And similarly, if beta is the next one, or aleph beta is the next one, then if there are at least aleph beta plus 1 things, and at least aleph beta things, second orderist does not think that's formalizable in second order logic. So they cannot see it as a logical truth. However, when you start climbing up further, so alpha and beta are going to be countable ordinals here. But when you start going further, there are some higher claims of this sort, claims involving higher cardinalities, that will be logical truths according to the second orderists. So for example, if there's at least aleph omega 1 plus 1 things, then at least aleph omega 1 things, where omega 1 is the first uncountable ordinal. That is second order formalizable, so that's a perfectly respectable second order logical truth. Logical truth as the second order sees it. Where I is the first inaccessible, that's definable in second order logic. I mean, you can define that using second order set theory effectively. A kind of second order version of the second order ZFC axiom. So you can define the notion of inaccessibility of being an inaccessible cardinal, and of course this is a much higher cardinal than aleph alpha plus 1, or even aleph omega 1 plus 1. So you can define that if there's at least aleph I plus 1 things, then there's at least aleph I things. You can do the same thing for Marlow cardinals and so on. So what's the upshot? The upshot is that you've got a very strange pattern of logicality here, right? First order logic would draw the line after between finite and infinite. There's a kind of gulf between the finite and infinite. It can define all the finite cardinal quantifiers, but none of the infinite ones. And so on the right hand side of that column, you've got just a row, a column of sequence of yeses followed by a sequence of no's. Okay, so there's a break between the finite and the infinite. With second order logic, you've got this very strange pattern where you've got an initial segment of yeses, but then you've got a few more yeses dotted around the place, just depending on what it can define. And that's a very curious, that would be a very curious fact about logical truths. If some of them turned out, what is the reason for some of these being logical truths and the great majority of them not being logical truths? I mean, it's just a very kind of haphazard kind of sequence. So I mean, that's not a kind of knockdown argument against second order logic, but it does kind of put pressure on it. And you might say, well, so what should be the pattern of yeses and nos? Well, of course, the infinitary logician that I've described takes logic to be maximally infinitary, according to that takes L infinity to be at least part of logic, will think that all of those are yeses. They're all logical truths. I mean, there's nothing special about the finite case, right? If there are at least alpha plus 1 things, then there are at least alpha things. That kind of should be true whether alpha is finite or infinite, if you understand. Alpha plus 1 is the next cardinality up. Okay. Right, there are generalizations of these bottom-up arguments. As I said earlier, it would be parochial to limit the applied logician's task to actual natural languages. Our linguistic inheritance is obviously contingent, so the applied logician's interest should not be in any particular natural language, including technical parts, but in its extensions. There's a typo there, that should be technical. That opens the door to generalizations of the bottom-up arguments that go beyond the countably infinite. So you could run the planets argument not just up to their countable infinity, but a much larger cardinality. Okay, so that was the shape of some of the bottom-up arguments. I haven't given you all the detail there, or I haven't given you them all, but I've kind of given you an indication of what they look like. And now let's move on to the last part, which is the top-down argument for the infinity of logic, infiniteness of logic. So the top-down argument is based on, addresses the question, starts off from the question, what is the nature of logic? An important feature of logic is its topic neutrality. And Tarski made the idea of topic neutrality precise by considering permutations. So if you just a very gentle introduction, consider the set ABC and a permutation mapping A to B, B to C, and C to A. Okay, so some sets, such as the set itself, ABC, they're mapped to themselves by this permutation. Okay, so they're invariant under the permutation, whereas others are not. For example, the doubleton AB is mapped to the distinct set BC. Okay, so it's variant, it's not invariant under the permutation. If we think of properties and relations as sets and define what it is for a property or relation to be permutation invariant, then we can answer that a question for particular properties and relation. So, for example, consider the property being Australian and the property being self-identical. The property of being variant, being Australian, is variant because there are some domains in which there are Australians and non-Australians, and so by a permutation or on that domain, you can map you can change the extension of being Australian. But not the property being self-identical. That's invariant because whatever domain you're thinking about, all the elements of the domain are going to be self-identical. Similarly, if we think about the relation of being human over the domain of all people alive today, well, that's invariant under permutation because all members of the set are humans. But it seems that being human isn't topic neutral. It's a bit more general than being Australian, but it doesn't seem a topic neutral property or thinking linguistically a predicate. So Guy Lecher's idea was to remove all sensitivity to subject matter, so building on Tarski, we must consider not just permutations of a domain, but bijections to others of the same size. So we can move to isomorphism invariant. Okay. So the idea is topic neutrality is spelled out in terms of isomorphism invariance across different models with different domains. And so it seems that a sufficient condition on the logicality of a relation, okay, so the next step would be to say that a sufficient condition on the logicality of a relation, a worldly entity, is that it's isomorphism invariant because it's topic neutral in a sense, right? If that's if you've got a relation like that, then it seems to be logical on this kind of topic neutrality criterion of logicality, which is a very kind of standard one. So how does that affect the one true logic? Well, an essay condition on the one true logic can be built out of this. If R is a relation over a collection of models of a logic L, and L is a candidate for the one true logic, for the correct foundational logic, well, it seems that if the relation is isomorphism invariant over the models, then the logic must contain an expression whose extension is equal to this relation in all the models. So we're not saying that all the expressions must be, must be part of the logic, that the logic must contain any expression for that relation, but it must contain at least one. So for example, think about being self-identical, because self-identical is a isomorphism invariant relation. The correct logic should include a term for it, a piece of language, an expression that will designate that relation. And assuming we accept identity as logical, then it does, right? So first order logic with identity, for example, includes identity by definition, and it does satisfy that condition for that particular isomorphism invariant relation. And the thought is, there's nothing special about identity. Why not include terms for all, or expressions for all the isomorphism invariant relations? And if you're pursuing the ambitious project, not parochial project of looking at a kind of fragment of meaningful discourse, then you should throw everything in to the one true logic, the correct logic. And by the way, this sort of largely bypasses the vexing problem of logical constants, which is to find a criterion that classifies non-self-identical as logical and is a male vixen or is a regular heptahedron as non-logical, right? So non-self-identical has the same extension as is a male vixen, and which has the same extension as is a regular heptahedron, namely the empty extension. But the thought is that non-self-identical is a logical constant, whereas is a male vixen is not, and is a regular heptahedron is not. Because is a male vixen, you need to understand something about vixens, whereas is a regular heptahedron, that's kind of a mathematical claim that there are no regular heptahedra. Now, I do think it's a vexing problem. We don't have a good account of how to distinguish the logical constants from non-logical constants, but I think we are much safer ground when we're talking about the relations of worldly entities, and I think we can say, I think it is a very reasonable criterion of logicality there, sufficient condition that they are be isomorphism invariant, and then all you need is just one entity that denotes one expression, that denotes that particular relation. So non-self-identical will be part of the one true logic, and is a male vixen, may or may not be, or is a regular heptahedron, may or may not be. That may or may not be a logical term. I mean, I said intuitively they're not, but we don't really need to rule on that. We just need a kind of an expression for the relation that these all denote. Okay, so another step along the kind of road to the maximal infinity of infinitary of logic, of the correct foundational logic. So my title was, why is infinitary logic generally logical? But I mean, it's a sort of, in a way, my claim is stronger than that, because I'm claiming that it's not just infinitary logic that's logical, but at least L infinity is generally logical. And in fact, in the book, we go even further. So the claim is that a very strong form of infinitary logic is generally logical. So part of another moving part here is a theorem proved by McGee, which links this notion of invariance to the infinitariness of logic. Because so far I've just talked about the logicality of relations, but McGee links this to a particular logic. This is an article by McGee from 1996. And the rough version of the theorem, I'm not going to go into more detail here, is that a property or relation of the right type is isomorphism invariant just when it's expressible by a formula of L infinity. And this logic L infinity is in a sense as infinite as can be. I mean, as explained, it extends first order logic by allowing conjunctions or disjunctions of kappa many conjuncts or disjuncts for any kappa, and by allowing quantification over kappa many argument places for any cardinal kappa again. And so, in one true logic, we prove the version of McGee's theorem for this logic that I mentioned earlier, FTT infinity. And this is the generalization of first order logic along two dimensions. First, from first order logic's type to all finite types. So you don't just have the type of individuals or properties of individuals, but properties of individuals, and properties of individuals, and relations of individuals and individuals, and relations of properties and individuals, and so on. And along the second dimension, from finitary conjunction or disjunction to an existential quantification to their respective maximally infinitary versions. You can conjoin or disjoin any collection of formulas you like, and you can existentially quantify over any set of variables, however many there are, any kappa size set. And this is what this version of the theorem looks like. If R is a relation over these models, then for all these models, M1 and M2, and isomorphisms pi between them, if pi is an isomorphism from M1 to M2, then Rm1, the interpretation of R in M1, gets mapped to the interpretation of R in M2 by pi, if and only if, for any domain, for each of size kappa, for each non-zero cardinal kappa, there's a formula of this language, such that if the domain is of size kappa, then the interpretation of the relation just is given by the interpretation of the formula in that particular model. Okay, so okay, let's just, I'm almost done. I'm just going to run through the schematic form of the top-down argument. Okay, it starts off from the claim that logic is topic neutral. The clearest, cleanest, and most convincing way to understand topic neutrality more precisely is as isomorphism invariance. And it turns out that this notion of invariance coincides with what can be characterized in a highly infinitary logic. So the one true logic, the correct logic, stands to its finitary version as L infinity infinity does the first order logic. So in particular, if like virtually every logician, you accept first order logic as part of the one true logic, or even logics if you're a pluralist, then you should also accept L infinity infinity. Okay, so that's the upshot, the top-down argument for logic being infinitary. And just to wrap up, how do the top-down and bottom-up arguments work together? Well, they seem to combine very nicely. They seem to point to the same conclusion, namely that logic is infinitary, indeed that it's highly infinitary. So I'll stop there.